Hi, I'm Rodney, and I'm going to share a strategy, a meta, for going from edge orientation to domino reduction that I think is, in some sense, optimal. If you're just interested in the TLDW, no worries, here it is. But if you want to dig into the statistics for what justifies this meta, then let's go. So if you're going from edge orientation to domino reduction, there are about 1 million visually distinct states that you can have. That's too many to keep track of, so we need to group them into subsets to make sense of them. You can write code to count them all, which all this analysis is going to be based on code that Louis Sarthau wrote to count the states, and then we're going to be figuring out what are the optimal subsets that we can group them into. So first, let's go over how we're going to identify subsets. So first is the DRM number, so DR minus, so that's the number of corners and edges that are out of DR. So this would be 1, 2, 3, 4, 5, 6, 6 corners, and then I have 1, 2, 3, 4. So 6C, 4E would be the DRM case, DR minus. And if you're looking on inverse, the DRM is the same. So on inverse, this will also be 6E, 4E. The second number is the AR minus. I have a video on axial reduction. But the AR minus number is the number of yellow-white stickers on the RL faces. So this would be AR 5C. And then the edges is the bad corners in the M slice. So this is 5C 1E. And then to get the inverse, it's not going to be the same. You have to count the red stickers on the white face. So this would be AR on inverse. This would be AR minus 4. And then the AR edge number will be all the non-red bad stickers here, which is the same as looking here and looking at the bad slices, the bad edges in this slice. If you had R on top, or you can count those. So this will be 5C1E is the AR minus number, the ARM number. Now, the other important thing that people use to talk about these subsets is counting pairs. So pairs is, here's a bad edge, bad corner with the U facing away. So that's a pair. This is another pair, so that's 2 pairs. This is not a pair. This is a fake pair where it's bad, but the yellow's sticker is right next to it like that. And then to find those on inverse, you find a bad pair. So this would be like white, orange. And if I can find a white, orange, a bad corner that has white, orange here, but not with those stickers on the side, then that will form a pair. If I found white, orange, like where those 2 stickers are here and it's bad, that would be a fake pair. And then the last thing is going to be side pairs. So here's a side pair where I have these UD stickers on the side like that. And to identify side pairs on the inverse, you look for bad edges. So here's a blue-red. If I can find another blue-red with the same color on top, so there's blue-red, this is going to be a side pair on inverse. When you're looking for DRs, you have to manage your time. If you want to be perfectly thorough, you would check every EO or every 5-move extension of an EO for the optimal DR to see if it meets your objective. Let's say my objective is a sub 7. So 5-move EO, sub 7 gets me to an 11-move DR, and that's my objective. But if I were trying to be that thorough, I'll run out of time. The most time-efficient thing is to only look for things that you have pre-memorized. So you can say, oh, I know a few cases, and if I hit one of those cases, then I'll just look for those. But you might end up not finding anything in that case because those cases might be pretty rare. So statistically, this is a balance between recall and precision. So recall is a measure of how thorough am I being? In other words, how many of the states that meet my objective am I checking? And then precision is kind of a measure of how easy it is to find. One thing I picked up when I was sitting in the Worlds is that there were a lot of DNFs. DNFs are a recall problem. You can measure the recall for any subset by just counting how many solutions there are that meet your objective in the subset. So that is a measure of the recall, and then the precision is just given the subset, how likely is it to be to meet the objective. So this might be a high recall because there's a very 6C4E is very common. There might be a lot here, but they might be hard to find. Here they're easy to find, but this is a rare subset. So we want to balance between those two, and if we do that, we can do that by simply multiplying them together. And this is very closely related to the information theory quantity called mutual information. It's not exactly the same. It probably orders things the same. It's easier to calculate. I'm calling it the mutual info, and it's just the product of that precision and that recall term. So that's what we're going to use to kind of score our subsets and to decide whether they're optimal. Here's what you get if you just take all of the possible DRMs, compute their mutual info, which is just the product of these two numbers, and rank them. I have a definition of findability, and so I limited myself to findable sub-sevens instead of just sub-sevens. That's just that's a little refinement that changes this ordering a little bit, but not in a super important way, I don't think. So, but this was an aha moment for me because look at what pops out. What pops out is the most important DRM, 4C4E, then 3C2E, 7C80, 4C2E. If you had taken a poll of FMCers and asked them to rank the DRMs most important to focus on in a solve, these are the answers they would have given you. So the fact that this kind of a priori number pops out that answer means it must be measuring something real. And it also makes me think we should be looking at what comes after those top ones, because if it gets those 4 right, it's probably getting the next 6 right. So these are the top 10, and we're going to be digging into this. So every time you hit an EO, you have some options. The quickest thing you can do is just to decide to discard it completely and move on. This is suggesting that you should discard anything that's, say, not in this top list of top 10 DRMs. So this is already something valuable. But for these maybe unfamiliar cases, maybe there's something better that we can do. So the next most efficient thing you can do is just to see if it's a case you recognize. So this is low time investment. Maybe do some random moves, see if you get it to a case you recognize, and then if not, move on. The next most kind of thorough thing you can do is just try to find the optimal for the case that you're in, and if the optimal meets your objective, then write it down. And then finally, the most time-consuming thing you can do is decide to NIS. So this case, like this, if you just use the DRMs as your subset, none of these are. It's still too coarse. Like none of these are things you would NIS, except maybe this 3C2E. 60% is worth NISing, regardless. But you wouldn't want to NIS every 4C4E with only an 18% of finding a sub-7 solution. So the state of the art for subsetting these DRMs is arm pair counts. So that looks like this. So here's the arm pair sheet for 7C8E. People have a lot of people kind of contribute to this. Carter, Kale, Evan, Uradik. All kind of been working on these stats, but as you can see, there's quite a lot to digest here, and you can make it an effort. But what we're really going to be able to do is kind of cut through this. So here's all the arms cases, and this is just the precision number here. Somewhere there's kind of this is a number of cases, so we can actually get the mutual information for all these and do the same thing we did for DRMs, which is kind of rank all these cases and figure out the best ones. And then that will really help us limit the number of the stuff we have to pay attention to and digest. But we're going to go one step further, and instead of just computing all these combinations, we're going to use decision trees. Decision trees are a machine learning algorithm that will automatically scan through all the available features. And the features here are the arm number, the corner arm number, the edge number, the pair count, and we're also going to add in the side pair count and the fake pair count, and find out which one is actually most important for getting an optimal subset, where optimal means high mutual information. Decision tree look like? Here's the decision tree, the trained decision tree for 7C8E. And you can see that immediately it's dividing all the cases into subsets. So here's all the cases. This outer box represents all the cases. This represents all cases with 3 or fewer pairs, and this represents all cases with 4 or more pairs, which are further subdivided into 5 or more pairs, and then 4 pairs with an edge arm criteria. So this is a combination of the arm numbers and the pair counts. But what the decision tree training has told us is that right off the bat, if you don't have at least 3 pairs, you've got a less than 1% chance of a findable sub 7. And that is a huge, that's very easy to implement. You don't have to look at anything else if you can see that it's if it's 3 pairs or less, forget it. In terms of finding the optimal subset, so 7C80 on its own has 13.6% of a sub 7 findable. That's not enough to NIS, but if I look for which of these boxes has the highest mutual information, so here's the mutual info here, 432. If I look at the 4 pairs or more, then it's 817. And if I go actually to 5 pairs or more, that's 1156. So this is actually, according to our calculation, the optimal subset. 5 pairs, it's only 16% of cases, but that's still 3,800, so it's not that rare. And the probability of finding a sub 7 is over 50%. So this is definitely something that you would NIS on. If you let's look at some of the other cases. Here's the 3C2E, like 100% cases. If you just overall 60% of finding, can we improve on that? Well, if we restrict ourselves to things that have at least 1 pair, then we can get the probability up to over 80%. But actually, the mutual information drops here, so 1,200 to 1,000. So that means that yes, the probability is higher, but but the number of cases dropped by almost a factor of 3. So that's not enough to make this probability worth it. So we're still gonna we're not gonna subset 3C2E at all. Just NIS everything. Do search for optimal on the normal scramble. And that's what this analysis is telling us to do, which is kind of lines up with our intuition. Let's look at 4C4E. Again, this pops out kind of the intuitive result, which is kind of the, I would say, common wisdom now, which is that you shouldn't be NISing all 4C4Es. It's 18%. But if we look at which node has the highest mutual information, this one's 2,300. This one's 3,500. So you should be NISing at least 2 pairs. Any 2 pairs or more, that's 43%, and that's what you should do. And this is kind of I would say this is kind of the rule of thumb that most solvers use. Don't limit yourself to only 3 pairs now, and then you're down to 3.6% of cases. So 2 pairs for 4C4E. So those are kind of the cases that are known. So now we've established some trust in this analysis because it's given us an answer we believe in. So now let's see, what does it tell us for an unfamiliar case? Here's a 5C4E. On its own, 5.8%. But if we actually drill down, we can see, well, if we get 2 or more pairs, mutual information is still increased. And we're at 10%, but if we go to 2 pairs plus 2 side pairs, that's interesting, we can get it up to 18%. And this is actually the maximum mutual info. So this is the optimal subset here, 2 pairs plus 2 side pairs. Now, this is maybe not enough to NIS. Maybe it's not enough to search for optimal, but this is definitely high enough to be worth some random moves to see if it can get to if you can do like a couple random moves and set up a 4C4E, it's probably going to be a good 4C4E case if you start from 2 pairs here, and that's what this is telling us. So now we're starting to form a strategy on what to do for these previously I would say ignored cases. Based on whether you're in an optimal subset. Now there's one more refinement I can do to this subset calculation. Let's look at this 4C4E tree again. So what I was doing was looking through these boxes to find the one with the highest mutual information. that's good. But notice that I can maybe cherry pick something from this other side. So I found this big box here with 3517, and I found this is kind of the best box over in the other branch here is this one here, and it has a lower mutual information on its own, but I can plug this, N and this P in combination with this and compute what's the mutual information of the union of these two boxes. Even though they're not on the same branch, I can still define a subset which is these two boxes together, compute its mutual information, and see if it's greater than this one on its own. So that's a little bit of a pain, but doable. And what you find is, in this case, in fact, yes, these two boxes together are better than this box on its own. So what does that look like? So remember, this is two pairs. And what is this box? This is less than one pair, more than one pair. So this is exactly one pair plus two side pairs. Okay. So I can define my subset to be two pairs or one pair plus two side pairs. Now, suppose I do the same thing over here. Let's say for 5C4E, I can look at this and I can say, well, remember my best box on its own was this one with two pairs plus two side pairs. But let me cherry pick the best box from this other branch, and that's this one, which is exactly three pairs. Oh, so check this out. So this means for forming an optimal subset, I can either take two pairs plus two side pairs or three. In other words, two side pairs is as good as a single pair. That's what this is telling us, right? Because if I can define my subset as an either or, and in fact that's exactly what I did here. I can either have two pairs or one pair plus two side pairs. So this is the rule of thumb. Two side pairs is as good as one pair. And if you look at the other trees and you do this calculation, you see the same thing everywhere. You see the same thing everywhere. Two side pairs is equal to one pair. So very intuitive rule that falls out. We're just going to fold that into the meta. The only thing it doesn't apply to is this 7C8E. With 8E, the whole E slice is a bad pair edge, so side pairs don't really make sense. But you do find that if instead of 5 pairs, you can have 4 pairs plus an edge arm less than or equal to 1, and that gives you the optimal subset for 7C8E. So this gives you so now we're ready to go on to the meta. All right, so here are the recommendations that fall out of this whole analysis. And you can see some very familiar rules in here and some unfamiliar ones. So 4C4E, NIS on 2 pairs, but with the new wrinkle that maybe one pair plus 2 side pairs is also worth NISing, and going and looking for optimal on the normal scramble. 3C2E, all cases good, continue. Maybe a simpler rule than some people using 7C8E typically use. Just count the number of pairs, 5 pairs, or this equivalent, 4 pairs plus edge arm, 0 or 1. Here's another kind of rule for 4C4E that maybe more people aren't using, 1 pair plus 1 side pair, where you could use 2 pairs instead by just substituting 2 side pairs for 1 pair. And then after these familiar DRMs, we have all these kind of different cases where there's a suggested action other than just giving up. So in particular, if it's a hard scramble, if you're looking for an alternative rather than going to like 6 move extensions of EO, this is suggesting that it's time worthy investment to take these 5C4E, 5C6E. Interestingly, 4C6E falls into this category, 6C6E, and this 3C4E, and invest some time just looking for quick setups. So finding optimal is maybe too hard for here, but if you can preserve some pairs, maybe form some pairs in 1 or 2 moves, set up a 4C4E, 3 or even 3C2E, that will be a worthwhile time investment. As long as you've got the requisite number of pairs, 3 pairs, which of course could be 2 pairs plus 2 side pairs. This is an interesting thing that I'm keen to try out in practice. There's some more refinements in the doc, like this kind of breakdown about this one actually doesn't set up the 3C2E that much. This one doesn't set up to axial reduction that much. This one only sets up to axial reduction. So if you want to really refine that, you can like limit what random moves you're kind of trying to lead to. There's another refinement for breaking down the 4C4E by corner cases. The most interesting thing there is if you have 4B corners, you actually you need edge arm equal to 1 to have a decent chance of finding sub 7. So that's an interesting case. And then finally we get down to the first miscible non-primary DRM. Here is 2C2E, which with the pair is always worth missing. When we're down here, we're getting pretty uncommon, but it's great to have these alternative scenarios that you can use if you're having not a lot of luck finding good cases up in these really common DRMs.
So I'm quite excited to be able to make a first principles argument that reproduces the current meta for EO to DR, and also that you can then follow to make extensions and improvements on that meta. I took my best stab at suggesting actions for these obscure, lesser known DRMs, the 5C4E, 5C6E, 6C6C. But I think what's clear from the analysis is that there is unlocked potential in those DRMs, and I'm quite excited to see that potential unlocked.